Right. Hello. Um, I hope you're well. The thing I'm going to mainly focus on today for the next, I think it's going to be about an hour and a half rather than 2 hours, but we'll see how we go. Is chemistry calculation questions, which are the things that often people struggle with a little bit. Um, and that's really what the main focus is going to be. I can try and go around in other stuff, but just in the time that we have, it's hard to get through absolutely everything. So I've just sort of picked this based on what a few people said yesterday in terms of the calculations and these things, which if you're doing AQA is on paper one. If you're not, then it could be elsewhere. But ultimately, you need to be able to answer questions like this, although this is not actually a question because I've cut off the bit that matters. So, calculator ready. Um, I'm going to do quite a few of these questions so that we can try to just get used to the procedure that I follow, which may not be exactly what everybody do. If you let me know, because I think you said the biology revision that you just mentioned, which is vague. If you have any specific topics, then that would be helpful. And I'll try, but I'm not promising anything. Focusing on this. So the question here, which I've just taken from actually a textbook, so it's not an exam paper question, but it basically is what this says here, which is a bit of a mouthful if you're reading all of it. The question is basically what is the concentration of the acid used in this reaction, okay, which is the unknown concentration that it refers to in the question. So what is the concentration of the unknown acid? Now, look, when I do these questions, I try to simplify. Um, if you have a mock, just so you know, then you must know what the topics are on the mock. If you don't, then I can't help you. Um, what is the concentration of the acid used? So, this is how I always set up these questions. Okay, I always set up these questions. I like to write down in all of these questions, we have an acid and we have an alkali, just so you understand what titration is for those of you that might not be familiar with this. The principle of it is that if I've got an alkali here and I add an acid to it, then as you know, basically, acid plus alkali makes neutral, right? This will neutralize if you add an acid and an alkali together. But it's not as simple as that, because surely if I've got loads of really strong alkali and I put in one drop of really weak acid, it will not neutralize it. So the amount of acid that I put in to neutralize this depends on how strong the acid is, how strong the alkali is, and how much alkali I've got, right? There's quite a lot of things going into it. So what this topic tries to do is determine those answers essentially. So if I've got this alkali, this much alkali that's of this strength, how much acid and at what strength acid would I need to add to it so that it all neutralizes and balances out? And that's what we're trying to work out here. So when I do these questions, again, I recommend doing what I'm about to do, which always works. So let's just go with it. There's always going to be an acid and there's always going to be an alkali in the question. So acid, alkali. There will always be some information about concentration, about mass, and about volume. So I like to write down CMV. We're going to make a little table and gradually fill it in. There's also something missing in this question, which I need to get to. So we need the equation of the reaction. Um, so let me just get that first. So the balanced equation for this reaction, which I should have written first, is 2NaOH, because you will always get a balanced equation when you do these questions, because you need it, as you'll find out. So that's the balanced equation. There's the acid. You should know that that is the formula for sulfuric acid. And this is the alkali. That's sodium hydroxide. Anything hydroxide or oxide is a base, which is just a type of alkali. So this is essentially our alkali that is being added to this acid. The rest of it doesn't really matter, but we'll come to. This is not on combined. This is very much what we're doing today is mainly focusing on questions that are on triple science. But I will say some of this is. So the specific question may not be, but the things within this question that we're about to do, like the concentration equation, concentration is mass divided by volume, or as we're about to do in a while, calculate number of moles and things like that. Those individual pieces are in combined science, but it all kind of comes together in this kind of question, which is only a triple science question. Quite a difficult explanation. So when you write this kind of table down, let's start with that. Let's also write down the equations that we will possibly need to use. There is an equation in chemistry, which is concentration is mass divided by volume. We're going to need that. There is an equation, which is number of moles is mass divided by mR. That mass is mass in grams. We might need that. In fact, we probably will. So we've written down everything that I need now. What I'm now going to do is look at my I should also point out, by the way, if anybody's doing foundation level and happens to be here, there is very little quantitative chemistry calculations in foundation level science, so you know. In an experiment, this much sodium hydroxide. So what this unit is, centimeters cubed, is a unit for volume. Okay, so what they're telling you with that number is the volume of the sodium hydroxide. And as I said, the sodium hydroxide is the alkali in this question. So that's the volume of the alkali. So I'm going to go to my table, volume, alkali, and put 25 centimeters cubed there. I'm just going to fill this in. And as you'll see, it should work. It then tells you here the concentration of the alkali as well, 0.1. That unit is for concentration, is how strong it is, moles per dm cubed. That is a concentration of my alkali. Concentration, alkali, 0.1. Don't need all the zeros. Moles per dm cubed. That is the concentration of the alkali. Written that down. I'll also write down anything else, which is it is neutralized by this volume of acid. So that's the volume of the acid. So I'm going to put that there, 30 centimeters cubed. The question is to work out the concentration of the acid. So I'm going to put a question there. Do I think this will come up on any of my science foundation combined science yet? No. Simple answer, unfortunately. The concentration of the acid is what we're trying to work out. Let's do this now. So in basically every similar question that you get, you will have this much information in your table. Right, you will have basically two things on one side and one thing on the other side, and you will then have to just work around that. Let me tell you how we're going to do this. Because I know there is an equation connecting concentration, mass, and volume, because I've got concentration and volume here, surely I can work out this missing value. Because mass, if I rearrange this equation, mass is concentration multiplied by volume. You can see I do this in a very mathematical way. So mass is concentration times volume. So if I multiply those two numbers together, I should, in theory, get my m, shouldn't I? Because that is the rearrangement of the equation, except for one thing. The units here are different to the units here. So what I would like to do is change this to dm cubed. The way you change it to dm cubed is by dividing it by 1,000, because there are 1,000 centimeters cubed in 1 decimeter cubed. So I'm going to change this by dividing it by 1,000. If you divide that by 1,000, you will get 0.025 dm cubed. The numbers in these questions get really, really small. Don't be afraid of that. So 0.025 dm cubed. If I multiply these together, I will get my value that goes in here, because mass is concentration times volume. I've got concentration, I've got volume, my units are all correct. So if I times those together, it should be 0.0025, shouldn't it? Yep, it is standard form. 0.0025. Now, the unit of this answer, because we had moles per dm cubed and dm cubed here, the moles is the unit of this line. So we've got a value of moles there. We filled in our table. Remember, ultimately, we're trying to get to this value. When you do this, when you get a mass in moles of one thing in this table, you will be able to easily get to the mass of the other thing in the table. We're going to be able to do this. The way we do this is by resorting to the balanced equation. The balanced equation tells you that there is a ratio of 2 to 1 between the alkali and the acid. In other words, the acid is essentially half in terms of moles of the alkali that we need to use here. So if I've got this number of moles of alkali, then half of that is the number of moles of acid that I'm going to use. That's why this balanced equation is so important, because it gives you the answer. It gives you how you get from one thing in an equation to the other thing, because that's what these numbers represent. If it's a 2-to-1 ratio, it means that the number of moles of acid is half the number of moles of the alkali. So if I halve this number, it's going to be really small again. It gives me 0.00125. As I say, these numbers get really small, so don't worry about it. And again, that's in moles. So now I have the moles of the acid that I needed. We're nearly finished because we wanted the concentration of the acid in this question. We know there is a formula. Concentration is mass divided by volume to get to the concentration of the acid. I've got the mass and I've got the volume. The only thing is, that I should have written in the question, is that they will say they want the answer in moles per dm cubed. So they want the mass in moles and the volume in dm cubed. My volume is not. It's 30 centimeters cubed right now. So I'm going to divide this by 1,000 to turn it into dm cubed. That's 0.03. Clearly, I can just do this. But you may want to redraw your table very quickly. And they are my two values. The concentration is the mass divided by the volume. My mass is 0.00125. It is being divided by a volume of 0.03. The answer is that. And that's usually worth a lot of marks, that whole procedure. What I'm going to do next is, just now that we've given that, or I've done that sort of intro, I want to show you this in other questions. And I have various ones ready, but let me show you. I have access to this thing called ExamPro, which has lots of questions. And what we'll do, let me just pick a couple out. Focus on a calculation question. Right. Let me just go straight to this. I mean, this is only 3 marks, but it is the kind of thing that people tend to struggle with. But we can now use what we just did to do that. So same thing again. I know this is a part G of a longer question, but I don't think we need the earlier part, because I think we have everything we need here to answer this kind of question. And as you'll see, if you follow what I did earlier, it kind of all works. So we have an acid, that's there. We have an alkali, that's there. Because remember, sodium hydroxide, in the question earlier, it told you this is an acid. It tells it was citric acid earlier in the question. So that is the acid, that is the alkali. Let's write down acid, alkali, and then CMV for concentration, mass, volume. Let's fill in what we know. That is a volume, centimeters cubed, of the acid. Now, 13.3 centimeters cubed is the volume of the acid. Centimeters cubed. Now, in this case, what I'm going to do immediately now, because I know, I've done these questions a lot and you will get there, is that we don't like centimeters cubed. Most of the time, they want the answers involving dm cubed. So now I will just divide this by 1,000 to get 0.0133 dm cubed. Just saves me doing it later. So I've got a volume of an acid. This value is a concentration of the acid. 0.05 is the concentration of the acid. So I'm putting 0.05 moles per dm cubed there. What else do we know? That this was needed to neutralize this volume of the alkali, being sodium hydroxide. 25 centimeters cubed is the volume of the alkali. Once more, I know that generally I will always use dm cubed here. And so what I'm going to do is divide this by 1,000 now to get dm cubed. Let me see a question. Do you have calculation questions figuring out the limiting reactor? Yeah, I'll see if I can find one of those. That is a painful topic, the limiting reactant one a little bit. But I'll see if I can find one question on that. So the that is the volume of the alkali being used in this situation. So I've got all of the information I'm going to get. Remember, as I said, when you fill in this table, you will have 2 bits of information about one of them and 1 bit of information about the other one. That's always going to be the case. What we now need to do is remember some equations like concentration is mass over volume. I think that's all we need here. And I'm now going to work out the mass of this acid because the mass is the concentration times the volume. And because I've made my units correct, dm cubed, I can just multiply these two together. So we will have 0.05 times 0.0133 equals that. I'm just going to put it in normal form, 0.000665. Okay, very small, but it's fine. That is in moles because this was in moles. So that's your mass is always either going to be in moles or in grams, as I said yesterday, I think. But in this case, it's always in moles. Now that we've got it in moles, at this point, we can look at the balanced equation. And if you look at the balanced equation, remember, as I said, once you've got this moles of one thing, you can easily work out the moles of the other thing using the balanced equation. The balanced equation tells you that if I've got 1 mole of the acid, it reacts with 3 moles of the alkali. So to get from acid to alkali in terms of moles, we times by 3. It's 3 times as many, which means it's going to be 3 times as many as this number because this is the acid in moles. If I want the alkali in moles, I will times that by 3. And I get small numbers again, 0.001995. Okay, that is also in moles. So that's why we need the balanced equation to get from one to the next, right? That's why we need it. And now we're nearly done because the question is to calculate the concentration of the sodium hydroxide, which is the alkali. Concentration is mass divided by volume. I have mass and volume here. Let's divide them. Because I've already done my conversion and stuff of dm cubed, I will get 0.0798. And that will be the answer to the question, as hopefully will be demonstrated in a moment. Down there. So this is I'm asking for it, but the answer to the question was 0.0798. I just think that little table makes it much easier to understand what is going on in these questions. While I am here, I might try and see if I can do any of these, or if I want to do any of these other questions. Yeah, that's not that relevant. That's 5 marks, so let's have a look at this. Hey, a student titrated 25 centimeter cube portions of dilute sulfuric acid. So that's the acid. This is an alkali. Remember, I think that's easier on your mind rather than focusing on all these words. So there's an acid. That's the volume of the acid. That's the concentration of an alkali. Fine. And these are the results. So when you do this, you often repeat the experiment in reality. And what they did was they found that when they repeated it, it neutralized with these different amounts of the alkali. They've given you the reaction equation, as they always will, and they want the concentration of the sulfuric acid. Use only the student's concordant results. Does it tell you what they are? Yes, it does. Concordant results are those within 0.1 centimeters cubed of each other. Again, common-ish question recently I've seen a lot, where you get all of these different values, but you only want one of them. You want to calculate an average. You calculate an average by using results that are within 0.1 centimeters cubed of each other, which to me looks like these three. We don't want to win that. That's quite far away. That's one away, and that's way away. So no. So we're just going to use those three, and we're going to calculate an average using these three. So 22.1 plus 22.15 plus another 22.15 divided by 3. We're going to use 22.13. That is our volume of the sodium hydroxide. That's what we're going to use in our table, which I'm going to come to now. So let's do the same thing. The question is calculate the concentration of the acid. As you can see, often if you get into the swing of these questions, you don't really fully need to understand even what's going on. If you set it out, as I said, like acid, alkali, concentration, mass, volume, we should be able to just fill in the table as we have done several times already. We know the volume of the alkali we're using is 22.13 centimeters cubed. Volume of the alkali, 22.13. It's in centimeters cubed. I know that later I'm going to need it in dm cubed, so let's divide it by 1,000 now. It becomes 0.02213. That is 22.13 volume. Right, what else did it tell you in the question? That the volume of the acid was 25 centimeters cubed. So volume of the acid, 25 centimeters cubed, but let's again turn it into dm cubed. That's 0.025 dm cubed. So that should be dm cubed now. Then we have the concentration of the alkali, 0.105 moles per dm cubed. Or 105. Okay, that is the concentration of the alkali we're going to use. And again, the question says calculate the concentration of the acid. So you can see it's quite repetitive, these questions, once you do enough of them. We are now just going to do everything we've just done already. Okay, so formulas: concentration is mass over volume. We want to work out this mass over here, which is going to be concentration times volume. If we times these together, we should get our mass here. So let's do that. 0.02213 times, this is going to be really small, isn't it? 0.00232. That'll do. Okay, moles. You don't have to be perfectly precise about it. So 0.00232 moles. This is the point where we do that thing with the balanced equation. So we want to check whether, based on the equation, how many moles we have here based on the balanced equation. So once again, that's my alkali, that's my acid. You can see, I think it's the same equation we did at the beginning. It's a 2-to-1 ratio. Okay, 2-to-1. The acid is 1, the alkali is 2, which means that the acid is a half of the alkali. So to get from the alkali to the acid, I times by a half. Or divide by 2. And you get this number. This is what I mean by these numbers being really horrible. 0.00116. Okay, that is the moles of the acid that I'm going to get. The question is to calculate the concentration of the acid in moles per dm cubed. Concentration is mass divided by volume. I have the mass and I have the volume, so I can just divide one by the other. And I will get 0.046. And that is the answer to the question. So as you can see, they kind of follow the same procedure. I don't think I'm going to do too many more of those ones, but you can see this being virtually identical as a question. Yeah, I mean, it is virtually identical. There's quite a lot of these I've got, obviously. Okay, right. Let's have a look at or divide by two. Yeah. Yeah. Right. So let's then have a look at some other quantitative related questions that aren't specifically titrations. I'm going to see if I can just find one of these ones with a limiting reactant. But we've also got other topics within this, like atom economy, percentage yield. I mean, they're really easy, but you do have to know them. Let's see if I can find. Let me just do this because again, there's loads of different bits of quantitative chemistry that can often confuse people. But it requires an understanding that moles are quite important. So in the questions that we just did, as you saw, we were kind of already in moles. So we didn't need to switch from moles or something to moles. That isn't always the case. So this is a question that asks you to work out in a volume of chlorine gas. So iron chloride is produced by heating iron in chlorine gas. Here is the equation for the reaction. Calculate the volume of chlorine needed to react with 14 grams of iron. So this is how we do it. What we do first is what we need in this question. As well, to me, it gives you a quite nice step. It says calculate the number of moles of iron, then the number of moles of chlorine, then the volume. It's actually basically those steps that we need to follow. So we're going to work out the number of moles of iron used. So how do you calculate moles? You take the mass in grams and divide by the MR of the substance. Ions is 56, tells you conveniently. So to turn 14 grams of iron into moles, you would do 14 divided by 56, which is 0.25. Okay, so 0.25 moles is the number of moles of iron that we're using. Now, why do we care about that? Because ultimately, this question is about the chlorine. And because of the balanced equation, very similar to what we just did, if you know the number of moles of one thing in an equation, which we do now, 0.25 is the moles of iron, then we can easily use the balanced equation to figure out the number of moles of anything else in the equation. For example, because this 2 and this 2 is the same, if I've got 0.25 moles of iron, then I would have 0.25 moles of this iron chloride stuff if the question had asked it. But it hasn't. It asks for chlorine. Now, 2 to 3, I'm just going to go straight to it. What do you multiply 2 by to get to 3? The answer is 1.5, because 1.5 times 2 is 3. So what we're saying is that based on the moles ratio, the number of moles of chlorine is 1.5 times the moles of iron. So that means that the number of moles of chlorine is just this 0.25 times 1.5, because the number of moles of iron of chlorine is 1.5 times the number of moles of iron that I've already worked out. That gives you 0.375. So the moles of chlorine that I'm going to react is 0.375. Okay. The question, though, doesn't say calculate the mass or the moles of chlorine. It says calculate the volume of chlorine. And the last bit of this question gives you everything you need because there is a specific number, a magical number, 24, which is the volume of 1 mole of any gas. So if you have the number of moles of a gas by doing what we just did, you can easily turn it into a volume by just timesing it by 24. That's the answer to that question. Okay, so it's just understanding the relationship between moles and volume and the balanced equation. It's so fundamentally important that if I have the number of moles of one thing, I can easily work out the number of moles of any other thing the question asks me about. That was that. Was there anything else exciting in here? I don't think so. We could do a bond energy calculation. Nobody's very good with these. Um, yeah, why not? Come on then. Let's do it. Which is still not quantitative chemistry exactly, but it's part of the same area of the syllabus. Okay. And then I still need to find that limiting reactant stuff, which I will do my best to do. There's one in particular in my mind. I just need to see if I can find it. Right. The table below shows some bond energies. You have to calculate this missing one, and they have told you a very important sentence, which is that in the reaction, the energy released forming new bonds is 1034 greater than the energy needed to break existing bonds. Very important question, formula. The way chemical equations work, if you want a little quick explanation of what happens here, you have stuff on the left-hand side. And what happens to that stuff on the left-hand side is that it gets broken up. You break all of the bonds and break all of the pieces up. And what you do with those pieces is you make new stuff on the right-hand side, okay, using those same pieces. So a perfect example of that would be, if I can just quickly make up an equation, magnesium plus hydrochloric acid gives magnesium chloride plus hydrogen. It's not balanced, but who cares? Okay, fine. What that is telling you is that on this side, we had some magnesiums and we had some chlorines, two of them, hydrogen and chlorine. On this side, we've got, and so what we did to this side was we broke up these pieces so that we had like individual pieces of everything, and we just joined them up differently. So this magnesium joined with a couple of the chlorines, right? And then two of the hydrogens joined together. I think that was wrong. And then two of the hydrogens joined together to make that. So we've taken stuff from the left-hand side, mixed it all up, and made new stuff, but with the same stuff. Now, the point of this topic is that in order to break the stuff on the left-hand side, we have to take in energy, just as you would have to use energy to break a pen, something, right? You have to break, you're breaking something. It takes in energy. So the left-hand side of any chemical equation takes in energy to break it all up, which makes sense. The next bit makes less sense. On the right-hand side, we make new stuff with all of those pieces. When we make new things, energy is released. Okay, so energy comes in to break everything on the left-hand side. Energy is released when we make new bonds on the right-hand side. And that's kind of what this is trying to tell you, which is that, get rid of all of this. But in a chemical reaction, or in this particular reaction, the energy released forming new bonds, so energy released forming new bonds is 1034 bigger than the energy taken in to break existing bonds. Now, when you do these questions and you have to work out the overall energy change, what you do is you take the amount of energy taken in and minus the amount of energy released. So you take this number and minus this number. Now, if I'm telling you that this number is 1034 bigger than this number, then when you take them away, if you take this number and then take away this number, you're going to get minus 1034. It's a bit like me saying that this number on this side is 1035 and this number here is 1. So that number is 1034 greater than the other one. And if I do this number minus this number, I'm going to get minus 1034. That is a long-winded way of saying to you that what this sentence is trying to tell you is that the overall energy change in this reaction is minus 1034. That minus is really important that you understand it's a minus because we're losing more energy than what is coming in. That's why the energy released, losing, is more than the energy needed, taken in. Energy released more than taken in. So we end up with a minus energy change, which means it's an exothermic reaction. That's another story for now. What we need to do is understand how we would calculate this normally. The way you calculate this is you work out how much energy is taken in on the left-hand side minus how much energy is released on the right-hand side. So you do the left-hand side energy minus the right-hand side energy, and you will get, according to the sentence in the question, minus 1034. So what you now have to do is look at this picture and work out all the numbers on the left-hand side of these bonds, which are using these numbers here, and everything on the right-hand side. So it is quite fiddly, and you've got to be very careful. It's very easy to make a mistake on this, and I made it now. So what we're going to do is work out all of the energy needed to break all of this stuff on the left-hand side, and that's what these numbers are telling you. So on the left-hand side, we've got this HS. You see that HS there? Which they've told you is worth 364. Plus another HS, which is worth 364. We're adding it on. But then there's two of everything. So it's that. It's two times all of that. We'll work this out later. Plus, I want to have to make this, take the space up. So left-hand side minus right-hand side equals minus 1, 0. Then we've got these OOs. So there's an OO there with a double bond, which is 498. But the 3 in front of it tells you there's 3 of them. So that's 3 times 498. I'll work this out later. Minus. Right, now the right-hand side I have to do the same thing for. So we've got a HO bond there and another HO bond there. That's 464 plus another 464 times by 2, because the 2 in front of it tells you to do that. Plus, we've now got a double bond SO, which we don't know, interestingly. But if we did know, it would be X, plus another one that we don't know, which is X, and we're doubling it. So it's 2 times X add X. Again, you can see that this is very much mathematical. Right, I have created a question here, an equation, essentially, which is you've got your left-hand side minus your right-hand side, and we know the overall answer is minus 1034. So the energy taken in is all here. The energy released is taken in here. And we know the energy released is 1034 bigger than the energy taken in, which means that when you do one minus the other, you should get minus 1034. Now this is really a maths question, so it really depends on your maths and calculator ability. So on the left-hand side, what do we have? We've got 364 plus 364 there, times by 2, which is 1456, plus 3 times 498, which is 2,950. Okay, minus the right-hand side now. We have got 464 plus 464 times 2, which is 1,856. I'll write that down. Over here, we've got X add X, which I want to call 2X for the purposes of maths, times the 2, which is 4X. Okay, and I've just created an algebra situation here, which should be easy enough to do with one exception. There's one easy thing that you can get wrong, which I've almost made just now, which is that when you have minus the right-hand side, and you're minusing everything on the right-hand side, and you're minusing everything on the right-hand side, you need to try and keep it in a bracket, because that minus will make this a minus, and it'll make this a minus as well. So just watch out for that. 2950 minus 1856 minus 4x equals minus 1034. From which, this, again, shouldn't be too hard to do, but if I work out 2950 minus 1856, I get 1094. If I also just add this 4x to the other side to make it positive, get that. Then I can add this to that. And you get 2128. And then this x, which you're trying to find out, is that divided by 4, which is 532. Very long question, but that is how you go about doing this. As soon as you see a bond energy question where that's the thing that's missing, the x, there's an x inside this table, it's a bit of a pain and it's quite complicated. If it gives you this number, whatever it was, 532, and it just says calculate the overall energy change, then it's much easier, because you just do work out all of the numbers for the left-hand side and then minus the number for the right-hand side. And if that had been the number here, you'd have got minus 1034 as the answer to that particular question. Okay, let's move on. See if I can just find a maths question. There we go. Oh, not quite the same question I was after, but I'll try and figure it out. Okay, this is not quite as bad as a limiting reaction question can get, but still, it helps with your understanding of it. So we have, don't worry about the stage number, 40 kilograms of titanium chloride reacting with 20 kilograms of sodium. Explain why titanium chloride is the limiting reactant. Okay, so let's just rewrite the important bit. The important bit of the equation is the two substances that we care about, the titanium chloride and the sodium. Now, we have got, I'm going to change this to grams just to keep it correct. Okay, 40,000 grams of this, and we've got 20,000 grams of this. Fine, grams. In most calculation questions, you do not really want to be working with grams. You kind of have to turn them to moles. So let's do that. Moles, as we've seen already today, is your mass in grams divided by mR. That's why I changed to grams, because technically it has to be in grams. Do I need to do the mR as well now? Okay, well, sodium's mR is easy. It is just 23. Titanium chlorides is less easy because it is 48. That's one of the titaniums here. Plus 4 chlorines. That's 4 times 35.5. Which is 190. Okay. That means the number of moles I've got is 210.5. And the number of moles of the other thing I've got is 869. 870 roughly. Okay, it's fine. Now, the question now says, explain why titanium is the limiting reactant. And this is why. This is how much I am reacting with this. Okay. Now, according to the balanced equation, yes, the ratio 1:4, correct. According to the balanced equation, there is a 1:4 ratio between the number of moles of titanium that react with the number of the moles of sodium. So what we mean is that if I've got 1 mole of this, it will react with 4 moles of this. Okay. Let me just double check this. Making sure all these numbers are correct before I do the next bit. Oops. Okay, that's all correct. Yeah, so because it's a 1:4 ratio, that's 1, that's 4, we're basically being told that the amount of that would react with it is 4 times the amount of that would react with that. So 210.5 times 4 is 842. Okay. So what we're saying here is that if I've got this much of this, it will react with 842 moles of sodium. That's it. It won't react with more than that. But we've got more than that, you see? We've got 870 moles of it, which means that we've got too much sodium than we need, or not too much, but more than what we need. Because if I've only got 210.5 moles of titanium chloride, it can only react with 4 times as much. So 842 moles of sodium. It can only react with that much. But we've got more of it. And therefore, we will have some sodium left over, and this will be called the limiting reactant because it will run out of that. All of this 210.5 is definitely going to react because we've got more of the other one. Okay, so the limiting reactant is the titanium chloride, which is what you're trying to explain. So the limiting reactant is titanium chloride because we have an excess of the sodium. We have 870 moles of sodium, whereas only 842 of it will react. So the limiting reactant is the one that runs out first. The sodium's not going to run out. We've got more of it than we need for this reaction. It's not going to run out. The limiting reactant is the one that runs out first. That's the crucial thing to try to remember. And that is an example of a limiting reaction question. It's not probably the one that you were after, because I know the one that people are usually after. It's just always difficult to find it at short notice. Yeah, I might as well just do this question if it's something ridiculously easy, so let's just do it. Yeah, I know we did some of these yesterday as well, but I'm just here now. And to be fair, percentage yield is, even though it's very easy, it's very specific to triple. Okay. Here is an equation for something. It says calculate the maximum mass of iron chloride, FeCl3, that can be produced from 11.2 grams of iron. The iron's here. Now, I appreciate there's more to the equation, but we don't need that one. So in these questions, when you get these mass calculation questions, there's only two things you need because you're asking about the mass of one compared to one of the others. So I always like to, again, make a little table thing, right? So I've got mass in grams here, which is 11.2 grams of iron. So I'm going to put that there underneath the iron. The question is, how much of this can we make? Well, we can't answer that question until we turn this into moles. So the way we turn grams into moles, once again, is dividing the mass in grams by the MR. The MR of iron is 56. They've told you conveniently in the question. Okay, 11.2 divided by 56 is 0.2 moles. The reason why we want to work out the number of moles of one thing in an equation is that we can use the balanced equation to work out the number of moles of the other thing in the equation really easily. This is a 2 to 2 ratio. That means it's just the same. So whatever the number of moles are of this side will be the same as the number of moles we produce there. If it had been like 1 to 2, then you'd double it. If it had been 1 to 3, you'd triple it. You see what I mean? It's just these numbers are important. But if they're the same, it just stays the same. So that means we are going to produce 0.2 moles of iron chloride in this reaction. And now, because the question wants grams of iron chloride, not moles of iron chloride, we need to turn this back into grams. Moles is mass divided by MR, which means that moles times MR will get us back to mass in grams. So we need to multiply this by the MR of iron chloride. The MR of iron chloride is 56, because that's the mass of the Fe, plus 3 lots of the mass of the chlorine, which is 35.5. Press equals, and you get 162.5. So we need to times that by 162.5, and you will turn the 0.2 moles back into grams, 32.5 grams. And that's the answer to the question. It says here the actual mass. So this is called a theoretical mass. So based on our theoretical calculations, we should produce 32.5 grams of iron. That never happens in reality. It says here the actual mass was 24.3 grams that we actually ended up producing. And there's a number of reasons for that, which you are meant to learn, like not all of something may react. You may have not measured things correctly, and various other things. The reason they specify maximum mass is because this would only happen if all of this 11.2 grams reacts. Okay, so that's why they specify maximum, because they're basically saying, or I'm saying, that if all of this 11.2 grams react, then we will make 32.5 grams. But it might not all react because there might not be enough chlorine for it to react with. Remember, we just did limiting reactants. We may run out of chlorine. We're assuming that we've got enough of this to make sure that all of the iron reacts with it. And so that's why it is important to understand that that's why it's a maximum. It just means that that's the most we might get. We might not get that much. Like if I've got all of this iron, right, but this much chlorine, then that's not going to result in that much iron chloride produced, because as soon as this is reacted, that's it. That's the end of the reaction. So we're not going to react all of the iron. We're just assuming that if all of the iron reacts, then we could get 32.5. That's why they put maximum. Okay. So what they actually produced was 24.3 grams. What we thought they might produce was 32.5 grams. They want the percentage yield. It's just like when you get marks in a test, right? You've got this many out of this many. What do? You do that divided by that times 100. That's all this is. Percentage yield is the easiest thing in the world. We expected to make 32.5. That's the full marks, as it were. This is what we actually got. Turn it into a percentage. 74.8. And that's it. That is how you go with that. The concentration questions I've just done, if you missed it at the beginning, then just you can rewatch it back. But I did about 4 or 5 concentration questions at the beginning. Atom economy, I'll just do something on now. If I can find anything immediately on it. Okay, let's do that. Full on equilibrium question as well that somebody else has asked about. So this question is about reversible reactions and equilibrium. Hydrogen is used to produce ammonia. In the Haber process, the hydrogen is made in 2 stages. Right, calculate the atom economy for the formation of hydrogen in this stage. I'll just tell you how you do it. Yeah, it will end up on YouTube. This morning's is on already, and this will be on later. And then there's one from yesterday that isn't, which I need to sort out. But all of these will end up there. So, if I'm going to go way off topic here to explain atom economy very quickly. If you remember a topic called efficiency in physics, in which you basically go, I've got an object like a fan, okay, and I put electrical energy into this fan, and it gives me kinetic energy because the blades spin, excellent, but there's a little bit of sound which is wasted. Now, if I put some numbers to this situation and said I put 200 joules of electrical energy into it, of which 150 turned into kinetic energy and 50 was wasted, and I said work out the efficiency from this situation, the efficiency is the useful energy that we get out, which is this 150, divided by the total energy that we put in, which was 200, and that's it, basically, and we times it by 100. But essentially what we've done is we've gone out of everything that we put in, what turned into useful energy. In this case, that was 150. The same thing basically applies to atom economy. It is essentially the same thing. We're going to work out that out of all of this stuff that I put into this reaction, how much of it turned into the useful thing that I was trying to make, which in this case, they tell you in the question, is hydrogen. So think of hydrogen as like the useful substance, and think of this bit as the wasted substance. And now it is essentially the same as an efficiency question, which I'll prove to you. What we do to get our numbers, I'm sorry, there's no numbers at the moment. The numbers that we need are the atomic masses of all of these things. So what we do is we go, right, what is the atomic mass of everything on the left-hand side of the equation? That's everything we're putting into this equation. So we've got CH4 here. That is I want to do this straight on the calculator, which I wouldn't recommend. A carbon is 12 plus four hydrogens. A hydrogen is one, so four of them is four, plus the H2O, two H's is another two, and the O is 16. That is the mass of everything that we put in. Think of that as the electrical energy that you put into the fan. Out of that 34, this bit turned into the thing I was trying to make, because this is all about the formation of hydrogen, right? Because that's what we're asked about. Hydrogen is basically the useful thing. So the useful thing's mass is, if we think of it this way, um, 3 times 2. So it's two hydrogens, which is two, but then tripled. You use the big numbers here. That's important. 3 times 6, right? So 6 is what we've got there. I could work out the carbon monoxide as well, but it's going to be the rest of it. It's 28, isn't it? Essentially, what we're doing in this equation is saying we don't need that bit. Okay. But what we're doing in this equation is saying out of everything that we put in, think of the electrical energy into the fan. Out of everything that we put in, how much of it turned into something useful? In this case, that's like my kinetic energy of the fan, or it's the useful product from this reaction. So out of everything I put in, 34, 6 of it turned into something useful. The useful over the total times 100 gets you to atom economy, just like it gets you to efficiency. It is very much the same concept, which is 17.6%. What is the difference between the purpose of atom economy and yield percentage? I find they are very similar. Well, they are. Yeah. Well, I don't know. Are they very similar? The purpose of atom economy is to say, if I was doing a chemical reaction, let's put it, you were doing a chemical reaction and you were doing, let's link it to biology just to mix things up a little bit. Let's pretend somehow, no, let's look at, yeah, biology, photosynthesis. Let's say you were somehow responsible for making glucose. I don't know how that works, but carbon dioxide plus water, right? And you were like, okay, I need to make glucose. I need to make loads and loads of glucose. If it turned out that, and to make glucose, you have to react carbon dioxide and water together. And I said to you, okay, well, if for every 100 units of carbon dioxide and water you put in, you're going to get 2 units of glucose and 98 glucose of units of oxygen that you don't want. It's a waste, right? So think of that as a wasted thing. You'd say, well, that's not great because that means I've got to use all of this stuff. I've got to spend all this money on my inputs, my carbon dioxide and water, to make only a little bit of glucose. That's not a great situation to be in. But we know that because the atom economy is 2 out of 100 in this case, 2%. It's really, really low. That's not great. Okay. So that gives you an idea for this reaction that it's not great because it's going to cost you quite a lot of money or quite a lot of inputs to get a small amount of glucose. That's one thing. That's atom economy, which is actually quite useful. Percentage yield is the bit that I think is rubbish. Percentage yield is just, okay, when I did a calculation, I expected that I was going to make 30 grams of some substance, glucose, whatever. But when I actually did it, I only ended up with 28 grams of it. My percentage yield is just what this number is as a percentage of this number. Percentage yield is the bit that I think is kind of rubbish because it relies on mistakes and things. But atom economy is just a fact. This is in this reaction, we get a lot of wastage and not a lot of useful stuff, or whatever it might be, whatever the percentage tells you. Whereas in this percentage yield, it's just, well, we thought we'd get 30, but because we made a mistake, we only got 28. So the percentage yield now is 28 out of 30 times 100. It's just a little bit of a pointless thing. I think the atom economy is more of a useful statistic, as it were. Okay, somebody else has mentioned about equilibrium. So while we're here, should we just answer these questions, right? So because we just happened to be doing a reversible, we coincidentally ended up with an equilibrium reversible reaction question in this topic. This is used to produce ammonia. This is the Haber process, which you are meant to know. Well, sorry, this is not the Haber process, but it's going to be used in the Haber process later. Explain why a low pressure is used in stage 1. 4 and 2. Because you get more hydrogen, it increases the yield of hydrogen. Let me explain. Just check that's the answer. Okay, yeah. So in equilibrium or reversible reactions, there is a important. So I'll try to fit it all on one screen, but I can't. So idea, which is that if you have a reversible reaction at equilibrium, the way you get asked questions on this is what happens when you increase the temperature and what happens when you increase the pressure. It's basically always the same questions, okay? Or what happens when you change the pressure. Now, because this question is about pressure, let me just explain how you know what happens in a reversible reaction when you change the pressure. If you increase the pressure of a reversible reaction, you end up making more of the side with fewer gas molecules. That's a bit of a mouthful. Let me say it again, right? When you change the temperature or the pressure of a reversible reaction, you end up with more of one side than the other. You produce a bigger yield of one side than the other. Because the idea of a reversible reaction is that it gets to a point where everything's balanced and the speed of one reaction forwards is the same as the speed of the reaction backwards. So you get to this point where you don't change the amount of stuff you're making. And that's when you have to introduce things like temperature and pressure because they help you change the amount of one side. If you increase the pressure of any reversible reaction, to find out which side you get more of, you need to do some counting. You count the number of moles on each side. On this side, there is one there and one there, which makes 2 altogether. On the other side, there is one there and 3 there, which makes 4 altogether. If you increase the pressure of this reaction, we get more of the side which has the lower number that I just worked out. So if you made the pressure really high, you would end up with more of that side, the methane and the water, that side. But that's not what we're trying to do, right? We're trying to make hydrogen here. That's the whole point of this. We're trying to make hydrogen. So if I use a low pressure, I would move it more to the other side. That's the point. The higher the pressure you use, the more it goes this way. The lower the pressure you use, the more it goes this way. That's a converse, right? So higher the pressure, you move to the lower numbers side. Lower the pressure, you move towards the higher numbers side. Someone's asked a question. I'll come to the endothermic, exothermic in a second. So that's related to temperature. Okay. So in this case, if I wanted to make lots and lots of hydrogen, I would use a low pressure because that would move my equilibrium to the right-hand side. It would give me a bigger yield of hydrogen. So when a question says, why is a low pressure used here? It's because a lower pressure gives you a higher yield of hydrogen, because that's the thing you're trying to make. Surely you're going to try and make more of the thing you're trying to make. And that's what we would do here. Probably is a 2 marks here. High yield of hydrogen because the equilibrium moves to the right. Is probably what you have to say here. Yeah, because there are fewer moles on the left-hand side. Remember I said that it's that the side with fewer moles is the side that we go to with a higher pressure. And if you go to the if you use a lower pressure, you go to the side with more molecules. So that's basically what this is explaining here. There's more molecules on the right-hand side. That's why we get more of the hydrogen. Then, in stage 2, they've asked the same question, basically. What is the effect of increasing the pressure on the equilibrium yield of hydrogen in this reaction? This is a different reaction, stage 2. Well, like I just said to you, the way you know what happens when you change the pressure is that you get more of the side with fewer gas molecules. Which side has fewer? Neither of them, because there is one on this side, or two on both sides here, aren't there? So one there, so two on that side, one there, two on that side. If it's the same on both sides, nothing happens. There is no effect of increasing the pressure, which is probably what the answer says. No effects on the yield of hydrogen. Okay, no effect. Excellent. So that is that. And then, I mean, I'm not going to do that, but let me just answer the question about. I'm not going to go into all of these. There was a question about how will you know which direction is endothermic or exothermic? As I know, they can vary with the. Well, the simple answer is there'll be a clue in the question. So if it doesn't explicitly tell you, so often questions do explicitly tell you which way is endothermic, which way is exothermic. So they will often say, let's use the Haber process as an example. The Haber process is nitrogen plus hydrogen gives ammonia, and it's balanced like that. And the Haber, which way is endo? I can't remember now. It is exothermic that way. Okay. I mean, as in it is exothermic that way. For the Haber process specifically, if you're doing triple science, this particular one, you need to know that it's exothermic that way and endothermic that way. And endothermic that way, which means that if you increase the temperature of this reaction, you get more of the endothermic side. That's what the rule is for equal reversible reactions, that the higher the temperature, the more it moves to the endothermic direction. Which means that in this reaction, if I wanted a lot of ammonia, which is what we do it for, you would use a very low temperature. The lower the temperature, but then that has its own problems, and you learn about that. But if it was any other reversible reaction, they should tell you which way is endothermic or exothermic, or they may say something like that. Okay. If you see something that looks like this, what it's trying to tell you is that the change in energy as we go from left to right is minus 200. That means it is, if we're losing energy left to right, it is exothermic left to right, which means it's endothermic right to left. So there's got to be a clue if it's a reaction that you've not heard of before. So for the Haber process, this one, you should know which way is endo and which way is exo. For any other reversible reaction, there should be a clue. And often the clue is quite small, and it's like this little thing here. That's exothermic left to right, which means endothermic backwards. Or it's just going to explicitly be told to you. Right, is there anything else? Let me just pick out a couple more questions. Good that. Okay, I think I might do all of this question. Right. Well, firstly, just while we're here, I think I did this. Did I do this? Yes, I don't think I did. But this is something that, regardless of what level you're at the moment, you will need to know this kind of thing. This is a required practical, actually, involving the salt crystals and stuff. A student investigated the reactions of copper carbonate and copper oxide with dilute hydrochloric acid. In both reactions, one of the products is copper chloride. Describe how a sample of copper chloride crystals could be made from copper carbonate and dilute hydrochloric acid. So, 4 marks to basically pretty much explain the required practical. So what you would do is you add the copper carbonate to the acid, and this next bit is important, until the copper carbonate, CC, is in excess. That in excess is important because what we're trying to do here in this required practical is make sure all of the acid gets used up. We want the acid to be the limiting reactant. Okay. So we add copper carbonate to acid until copper carbonate is in excess. Then what we do is we will have a solution that has copper chloride and water, because it's a neutralization reaction, and some unreacted copper carbonate. We want to remove the unreacted copper carbonate. So filter the unreacted copper carbonate. That's fine. Then what we're left with is some copper chloride and water. How do we get rid of the water? You heat the solution, possibly mention an evaporating basin if you like, until the water evaporates. And then leave it to cool. And you should get, magically, some crystals. Someone just said, explain how copper conducts thermal energy. It's because the particles gain kinetic energy. They then collide with the particles next to them. So these particles gain kinetic energy because they're being heated up. They then vibrate more. They collide with the particle, their neighboring particles, causing them to start moving, which then collide with their neighboring particles, and that causes the heat to be conducted. Thermal energy is heat to be conducted through the thing. Right, done. Move on. Right, the student wanted to make 11 grams of copper chloride. The equation for this reaction is shown. Calculate the mass of copper carbonate. The copper carbonate is here. The student should react with dilute hydrochloric acid to make 11 grams of copper chloride. So the copper chloride is here. We basically would like to make 11 grams of this, 11 grams of copper chloride. We need to know how much of this should we react to end up with that. The balanced equation is here, which is great, and it's a 1-to-1, which makes life very easy. There's nothing much to do here. And then we're going to, as with any of these calculation questions, convert the grams to moles, because we want to do that. So we want moles here. How do we convert grams to moles? We divide by the MR. The MR of copper chloride is, use the numbers in here. So a copper is 63.5 plus 2 chlorines, that's 2 lots of 35.5, which is 134.5. So 11 divided by 134.5 is 0.0818, roughly. Doesn't really matter because it's a 1-to-1 ratio, the number of moles that we need on this side is exactly the same. Remember, if it was a 2 or a 1, then you have to multiply and divide or whatever. But it's a 1-to-1, so nothing to do. We now need to convert these moles back into grams. How do you convert moles back to grams? You multiply by the MR of this time copper carbonate. So let's do that. Copper is 63.5 plus the carbon, which is 12, giving you everything in the question, plus 3 oxygens, which is 3 times 16. Cheers, 123.5. So let's times that by that 0.0818, and you will get 10.1, which is the grams that we should react of copper carbonate to make 11 grams of copper chloride. That is what we should do in that particular question. Hopefully that is helpful. There's a lot of calculation being done here. Okay, not doing that. Um, yeah, I'll do this because it's quite actually surprisingly quick. I've done the hard work for you. The percentage atom economy, there is a formula. Remember, there is a formula for this stuff. I don't think you should need a formula. If you understand that atom economy is very similar to efficiency, I don't think you really need to think of it in terms of an equation because it's just everything on the left-hand side on the bottom and then the useful product on the right-hand side. So I need more, actually. I need to go back to that question. So we're trying to make copper chloride. Okay, it's quite important because the copper chloride becomes the useful product from earlier in the question. It says calculate the percentage atom economy for reaction two. There's reaction two. How do we do atom economy? We do the left-hand side MRs. So the left-hand side has 79.5. What's on the bottom? Plus 2 times HCl. So 2 lots of 36.5. So they've done most of the calculation stuff for you. You do not get an equation sheet for chemistry. On the top, we want the relative formula mass of the desired product. The desired product is the copper chloride, which is here, right? So we don't care about this bit here. The copper chloride has 134.5 as its mass. And so you just times that by 100, and that will be your atom economy. So 134.5, and then we've got 79.5 plus 2 times 36.5 times 100 is 88.2%. Okay, that would be your atom economy for that calculation. And then, yeah, forget it, right? Let me see if there's anything else. Otherwise, what I might just do, just to finish off this bit, is skim through or run through quite quickly a recent chemistry paper. I want to stick with AQA because that's usually what majority are doing, but it doesn't really matter. I'll stick with the triple science one just to talk about it. I won't do all of the question. I'll just talk through them and the kind of things to think about as you're doing these things. So, and then we'll be finishing about 4:30. Right, you may have seen this paper before, but you may not. So it'll be up in a second. Just a paper one. So all I'm going to do is just talk through it. Okay, maybe I'll pick a question if I really feel like it. We have this, which is asking you to describe the plum pudding model, which is what we thought the atom looked like in around 1909 before the there's not a silly question. So there's a question here about what's the difference between when you need to use the big and small numbers next to the compounds. I think the simple answer is that you never need to use the big numbers unless you're doing an atom economy question. I think that's the best way I can explain it. Otherwise, you don't use the big numbers to calculate the MR or the AR because the MR isn't the big number is not part of the MR. The MR and stuff is just the little numbers, not the number in front. But when you're doing atom economy, you then need to include that big number when you're doing your calculation. That's the only time I think, off the top of my head, it matters. The plum pudding model was the idea was that they believed that there was a ball of evenly spread positive charge with electrons stuck inside it. Something like that would be what I would say for that. I am not going to have time to go through anything else in physics for today anyway. I'm just going to go through this paper, and then that will unfortunately have to be it. But resist, I don't know what about when you say, well, you can message us separately about it, but can you go through resistance in physics? I don't quite know what you mean. Resistance is a thing in a circuit where it slows down the current, and that's it. And then there's other bits involving resistance, but in terms of just purely go through resistance, there's quite a lot. It depends. It's to do a series of circuits, parallel circuits, different components. There's quite a lot to it, possibly, but it'll be for another time. Um, Atoms contain electrons, neutrons, and protons. Write these in order of their discovery. I think it's protons, electrons, and neutrons are definitely last. I can't remember which of those two comes first. I think it's protons and electrons. Predict the number of outer shells electrons in an atom of tennessenes. Where on earth is that? Right. Oh, use the periodic table. Sorry, I don't have the periodic table open. You just look at what group it's in. So depending on what group it's in, you would be able to identify how many electrons it has in its outer shell. That's it. Yeah, I'm not doing that. Isotope abundance calculation. Probably should have done one of these, but let me just do this on a calculator in front of you to show you how simple this is. If you're doing an isotope abundance calculation, this is all you do. You'll get a table that looks like this. Take the number in one column, the 6, times it by the number in the other one, 7.6. Oh, 6 times 7.6. Add on the number below, 7, times the other one, 92.4. So basically times the rows that you have, but add them together at the end. So 6 times 7.6 plus 7 times 92.4. And at the end, just divide the answer by 100. And that's the answer, 6.9. That is how you do that. So multiply the numbers in the rows, add them together, divide by how many there are. Right. So let me answer a couple of these questions. I did explain how copper conducts thermal energy. Then somebody said metals are thermal conductors. I mean, yeah, they can conduct heat. If a piece of metal gets hot at one end, it gets hot at the other end. So it can conduct heat. I mean, most commonly that question is about electricity, but I just answered it because I answered the question that got asked. So yeah, okay, fine, we move on. This is a question about a required practical involving the energy changes. This is probably, in my view, the easiest required practical because there's not too much to it in the sense that we do a chemical reaction, we measure the temperature before, and we measure the temperature after, and that's kind of it. The other little key features of it is that we tend to use things like a polystyrene cup. They use things like a polystyrene cup, and then that makes sure, because it's a good insulator, it keeps the heat in. An independent and dependent variable, I'll give you a little tip here, which the people I've taught will know. When you get these things like a step-by-step process of a required practical, the independent variable is almost always in the last step. Step number 6 tells you repeat with different masses of ammonium nitrate. That is telling you the independent variable, because by definition, the independent variable is the one you change each time you do the experiment. So this applies to all three sciences, really. When you get a step-by-step process, then you get the independent variable in the thing at the very end. Okay, right. And the dependent variable is whatever you measure. So what are we measuring here? Well, each time we're doing it, we're measuring the temperature reached by the solution. All right, then there's some results. You got to plot the data. It should be easy enough. That's called uncertainty. Fine. And then this is that exact question, I think, that we basically just pretty much did, which is making the pure dry crystals of zinc chloride from zinc carbonate and an acid. You've got to make it clear that the acid you're going to have to use here is hydrochloric acid. That will get you a mark just for specifying it, because it doesn't tell you in the question. And to get zinc chloride, you're going to have to use hydrochloric acid to do that. Anything else here? There's a bond energy calculation here, which is relatively nice because nothing to do here. There is a question about completing, and I think it's an exothermic reaction. Yeah. So if you're doing this for an exothermic reaction, do make sure that you draw the line below where we started. So depending on like that. Make sure it goes lower than where we started. Um, there is that. Dot and cross diagram of hydrogen chloride. I mean, hopefully it's too easy enough. But chlorine is in group 7 of the periodic table, which means that we have 7 outer shell electrons. 1, 2, 3, 4, 5, 6, 7. Hydrogen only has 1 electron, which means it wants 1 more. There's your hydrogen. There's the 1. It shares it, which means that this hydrogen's got 2 full outer shell. This has got 8 full outer shell. Hydrogen chloride drawn. Not doing that for now. A weak acid, if I remember, just means that it partly ionizes in water, whereas a strong acid fully ionizes in water. Um, I didn't get to this because I didn't talk about it, but in a titration, we always have an indicator which tells you when you have neutralized it. We don't use universal indicator. There are 3 other indicators that you can choose from. One's called litmus, one's called methyl orange, one's got a long name beginning with P. But they have different color changes depending on whether it's in an acid or an alkali. You do need to try and remember those. And the formula of the ion that makes a solution alkaline is OH minus. This is a calculation question, which I could have done earlier, but I shouldn't need to. I think it's one that you should go away and try and do. Because if you can see now, based on what we did earlier, that if you do one of those little tables where you do acid, alkali, concentration, mass, volume, fill in the information that you were given here, then you can fill in the rest of it. And that and also this question makes it even easier because it kind of gives you a step-by-step process as to what to do. But I just don't think you need to worry about it. But remember, most of the time, nearly all the time, the centimeters cubed needs to be changed to decimeter cubed by dividing it by 1,000, almost always. Well, which indicator you use? Not in this question, because it says name an indicator, and that's it. So there's 3 of them, and you can do that. If you look at the mark scheme, it'll give you all 3 as options. You do need to know the color change for the indicator you'd use. Like, for example, that phenolphthalein or something goes pink to colorless or something like that. But you do need to know the color change for the indicator. But which indicator you choose doesn't matter. I think litmus is easier because most people know it's red and blue because of the paper. Right. Unfortunately, I have reached the end of time for today. That is it. Hopefully, if those of you who have attended most of it have found it useful. What I did today will be on YouTube. If you have other questions, just generally, this goes for everybody apart from not just the students that I teach regularly, but through our social media stuff on Instagram and stuff, you can send a message, and if I have time, I can try and reply. But feel free to do that. I will try and do more of these in the lead up to the exams. So that will now be probably early May. In a few weeks' time, there will be more of these. There's almost always, just for those of you who are doing biology, there's always one I do the night before the biology exam that's available to everybody for free. So look out for that. And then there's other ones that I do, but they won't always be free. Right, I'll let you go.